Hey, what's up guys? Ricardo here, and today we have a tutorial on SN1 vs SN2 reactions, and learning to distinguish the two, and learning what favors which reaction pathway. Alright, let's jump right into it. So, first of all, let's cover the SN1 mechanism. And so, with the SN1 mechanism, just drawn out here, we start off with our sort of chiral center here. Or maybe not chiral, maybe the groups are the same. But anyway, we start off with this center with the leaving group. And first thing that happens is the leaving group is expelled, resulting in the formation of a carbocation. And so, then, the carbocation is then attacked by the nucleophile to form a racemic mixture of the R and S sort of enantiomer pairs, if the original group is chiral. And so the reason that this occurs and we have sort of a racemic mixture is because the nucleophile can attack from above or from below. And so we end up with either the nucleophile on this side here or on this side here. Next thing to note, which is important, is that the expulsion of the leaving group and the formation of the carbocation is the rate determining step. Now what that means is, we'll go over that in a second, but it basically means that the rate of reaction is dependent on this step and none of the other steps. And as such, the rate of an SN1 reaction can be described as K times the concentration of the substrate, and the substrate is sort of the electrophile here. And so what is a rate determining step? Now here's a little nice analogy which I like to sort of help conceptualize this. And so over here we have a bunch of sheeple. Now these sheeple really want to get the new iPhone at this sort of very snazzy looking Mac store. And so how are we going to let them get their gratification sort of faster? Here there's two gates in the way before they reach this iPhone heaven. And gate A is very narrow, but gate B is very wide. So do you think increasing the width of gate B is going to increase the rate of reaction? No, because they're all getting stuck here. Increasing the width of this gate isn't going to actually sort of make them get there any faster. However, if we increase the width of gate A, then suddenly all the sheeple can sort of race through and get there faster. So this is the sort of analogous to the rate determining step, where the sort of the formation of the carbocation here sort of it takes the longest amount of time. It's where the bottleneck occurs. The attack of the nucleophile occurs relatively quickly and without much sort of opposition once the carbocation has been formed. And so if we want to increase the rate of reaction, we've got to increase the sort of ability of the carbocation to form. So now let's jump into the SN2 reaction pathway. And so the SN2 pathway occurs in a concerted step, and it involves both the nucleophile and the sort of substrate. And so as such, the reaction can be written as rate equals K nucleophile, concentration of nucleophile, times the concentration of the substrate. And so this happens all in one step. The nucleophile comes in, attacks, the leaving group leaves, and then we've got the product over here. Now the important thing to notice is that there's an inversion of stereochemistry. Now it's important, opposed to the SN1 where there was a racemic mixture, SN2 results in an inversion of stereochem. And this is because if we look at it here, the nucleophile comes in this side, the leaving group leaves, and then the nucleophile sort of pops the groups over to the other side. Now a way to imagine this in your head is imagine like an umbrella sort of flailing about here, and then a really strong gust of wind pops it this other way. And that's the way to visualize it, and that's sort of what results in the inversion of the stereochemistry. So what are some factors that influence which pathway is going to be favored? One of the probably the most sort of important factors is the stability and the steric hindrance of the sort of carbocation or substrate. And so as you know, there's primary, secondary, and tertiary carbocations. So a primary carbocation is a carbocation with one other sort of carbon attached. Secondary's got two other carbons attached. Tertiary's got three other carbons attached. And you can also get a methyl with a positive charge. And so a tertiary carbocation is more stable than a secondary, which is more stable than a primary. And as such, which one do you think will result in a favorment of the SN1 pathway? Well, do you remember that the SN1 pathway was determined, the rate determining step was the formation of the carbocation. And so if we widen that gate and make the formation of the carbocation easier by making the carbocation more stable, i.e. a sort of tertiary carbocation, then the SN1 pathway will be favored. And so an SN1 pathway really prefers tertiary. It sort of can do secondary, but it'll be in competition with the SN2 pathway, and it will very rarely, if ever, do a primary. SN2, on the other hand, the determining factor of SN2 is to do with the ability of the nucleophile to reach the center of the substrate. Because as you remember, the nucleophile needs to attack the center of the substrate in order to pop the umbrella the other way. And so for it to do this, it has to be able to reach the center. And so the determining factor which limits or allows this is steric hindrance. Now steric hindrance is sort of the bulk of the groups and how they interfere with the ability of the nucleophile to reach the center. And so with a tertiary carbocation, these R groups sort of can be very bulky, and so either methyl groups are pretty bulky, especially you might even have sort of aromatic groups off here, and then you have a huge steric hindrance and you're very unlikely to get an SN2 pathway. A secondary carbocation, I mean, it's slightly sterically hindered, but it also is nowhere near as sterically hindered as the tertiary, and so it'll allow SN2 to occur, but it'll also be in competition with SN1. A primary carbocation, however, is very easily accessible to a nucleophile, and thus will be favored via an SN2 reaction mechanism. So for SN2, a primary substrate is better, a secondary is better than a tertiary. Moving on. The next factor which sort of influences which pathway is taken is the stability of the leaving group. Now, a more stable leaving group will sort of favor both reaction pathways. Because, you know, in both the reaction mechanisms in SN1 and SN2, we have to get rid of the leaving group. And that's why it's called the leaving group. However, in the SN1 reaction pathway, the expulsion of the leaving group is what allows for the formation of the carbocation. And so if we make that occur with less sort of energy and less resistance, it will heavily favor the SN1 pathway. So a stable leaving group will more heavily favor an SN1 reaction pathway. So over here on the left, we've got some examples of sort of strong acids. And in order to determine what a good leaving group is and what a stable leaving group is, we have to go back to our acid dissociation chemistry. And so here we have an acid HA dissociating into H plus and A minus. So what makes an A minus or a sort of leaving group more stable? Well, a stronger acid will sort of dissociate more this way and result in formation of A minus, and this A minus will be sort of thermodynamically favored and the products will be favored. And so if we take strong acids and we look at their conjugate bases, then there we can see good stable leaving groups. And so for example, hydrogen iodide, hydrogen bromine, hydrogen chlorine, and sort of hydroxide, they're all examples of strong acids, and their respective iodine, bromine, chlorine, and water will make good leaving groups. Alcohols and normal water, however, are very poor acids and won't dissociate much. And so sort of their respective leaving groups of OR and OH1 aren't very good leaving groups, and thus will sort of not favor the SN1 pathway. And by not favoring that, it's sort of, you're slowing down the rate of reaction a lot, because a weak leaving group is not going to favor sort of either of the reaction pathways, because both of them need to expel the leaving group. However, a strong leaving group will favor the SN1 pathway. So, right there, strong, or stable rather, leaving group favors SN1, unstable leaving group favors neither. Another factor which influences which pathway will be taken is the strength of the nucleophile. So, in which of the reaction pathways is the nucleophile important in the rate of reaction? Well, that would be an SN2. If we have a strong nucleophile, the nucleophile is going to be more likely to go into the center of the substrate and actually attack it, rather than waiting for the carbocation to form. And so a strong nucleophile like iodine, bromine, chlorine, and hydroxide here will favor SN2, while a weak nucleophile like alcohol, water, and fluorine will favor the SN1. Well, they won't favor the SN1, but they'll disfavor the SN2, and by virtue of disfavoring the SN2 will result in more of the SN1 pathway. And so you might be looking at these lists of strong and weak nucleophiles and be a bit confused why most of the halogens are over here in the strong nucleophile camp, while sort of fluorine is in the weak nucleophile camp. And the reason for that is to do with the sort of size and electronegativity of fluorine. Fluorine is very small, and as you know, it's the most electronegative element on the periodic table. And so it really wants electrons. And so if it's not really able to stabilize its negative charge given its small size. While iodine, bromine, and chlorine, they're all highly electronegative, but they're far larger in size, and so they're thus able to sort of stabilize their negative charge a lot better. While for fluorine, having a negative charge results in it being very unstable, and it would rather sort of share those electrons with hydrogen or another element. Now the last sort of thing to go over is the type of solvent in which the reaction is taking place. Now this could be beyond, the mechanism behind all this could be beyond the scope of your course, so it's not going to be covered in this video here. If you want to look into it, I'd suggest you type in polar aprotic versus polar protic solvents and solvent shells, and that'll sort of give you a rough idea of how that all works. But the thing to remember is that polar aprotic solvents favor SN2. They basically make it easier for the nucleophile to reach the substrate. And so if you see things like DMF, DME, DM sort of SO in your sort of reaction as sort of the solvent it's dissolved in, this should be sort of alarm bells ringing for the SN2 reaction pathway. So in summary, basically the SN1 reaction in terms of the substrate of the carbocation will favor tertiary more than secondary, which will be more than primary, and this will be reversed in SN2 because remember of steric hindrance. So remember for here it's the stability of the carbocation. For SN1 that's the sort of dominant factor. For SN2 it's the steric hindrance. Now a good leaving group will sort of favor both reactions, but it will favor SN1 more. So it'll favor SN2, but not as much as sort of SN1. A strong nucleophile will favor SN2, because remember, the nucleophile has to attack the substrate, while a weak nucleophile will disfavor SN2, and by virtue of doing that, favor the SN1 pathway. And solvent, polar aprotic, makes it easier for the nucleophile to reach the substrate, and so thus favors the SN2 pathway. Alright, here we have a few practice problems. So we've got some substrates here. I just want you to quickly write down which reaction pathway do you think would be favored sort of based on the substrate. Alright, so let's get into it. So first one here, we have a tertiary substrate. We've got an R group here, R group here, R group here. So when that leaves, we'll form a tertiary carbocation. Tertiary carbocation is for this most stable form of carbocation, and thus will favor SN1. Alright, over here we have chlorine attached here, and so what will happen when this sort of leaves is we'll have a secondary carbocation. So this sort of results in both pathways being favored. And so you will see a competition between SN1 and SN2. Over here, this leaves, and we have a primary carbocation with only one other R group attached. And so this will heavily favor the SN2 because the primary carbocation is not very stable and thus will not form, and there's not very much steric hindrance around a primary carbocation. Now, final one over here. This iodine leaves, will result in a secondary carbocation, and so you got competition. However, let's close that. However, we can see that when this leaves and we have a sort of positive charge here, this can be resonance stabilized by the benzene ring. And so it'll make the carbocation a bit more stable than a normal secondary carbocation. And so you might see a slight increase in the amount of SN1 reaction pathway in a substrate like this. All right, here we have some leaving groups. And so some nucleophiles rather. Here we've got some nucleophiles. And so which sort of pathway will each of these nucleophiles favor? Well, here we have iodine, which is a strong nucleophile. A strong nucleophile will favor the SN2. Here we have fluorine, a weak nucleophile. So that's going to disfavor SN2, and by virtue of doing that will favor SN1. Water. It's another weak nucleophile, so it's going to disfavor SN2 and by virtue of that favor SN1. Chloride is a strong nucleophile, so it's going to favor SN2. And alcohol is a weak one, so it's going to favor SN1. So here we got a slightly different style of question. Here we have a reaction profile, and the questions are asking us, is it SN1 or is it SN2? And what would be the best way to increase the rate of reaction? So pause the video here if you want to have a go at it and test your understanding. Alright, let's go into it. So let's sort of break down this reaction profile. Here we start off with some reactants, and then they sort of go up this activation energy, and then they form some form of a sort of stable intermediate here, as we can see in this little dip here. This stable intermediate that requires only a little bit more energy, and then it goes to the products. Now, which pathway, SN1 or SN2, has the stable intermediate? Well, I hope in your mind you're ringing out SN1, SN1, because over here will be the formation of the carbocation. And so carbocation is the stable intermediate. And so how will we best increase the rate of reaction? Well, we could make the formation of the carbocation easier. We could do this by, if the substrate is not already tertiary, making it tertiary. We could make it resonance stabilized. We could sort of make the leaving group a better, more stable leaving group. We could disfavor the SN2 pathway by putting in a sort of weak nucleophile. All these sort of things will help to increase the rate of the reaction of this SN1 pathway. Next question, is this one SN1 or SN2? And how would we increase the rate of reaction? Well, I guess by process of elimination. If the last one was SN2, I mean SN1, this one will be SN2. But let's break it down anyway. So here we start off with some reactants, and then we give them a lot of energy, and they reach this sort of high energy transition complex. This is the transition complex. And this is when both the nucleophile and the leaving group are sort of bonded, but sort of not. They're sort of both attached to it. And then we have the leaving group leave here, and we end up with the products. And so how would we best increase the rate of reaction? Well, with an SN2 pathway, we could make the sort of substrate less sterically hindered. We could decrease it to a primary carbocation. We could put in a stronger nucleophile. We could put it in a polar aprotic solvent. Do all sorts of things which make it sort of more favorable for the nucleophile to attack the substrate. And so that's basically a quick sort of walkthrough of the SN1 and S2 pathways and certain factors which favor either the SN1 or SN2 pathway. I hope it was somewhat useful. If you have any ideas on any other videos you want explained or had, please let me know and comment in the sections down below. If you got any suggestions on how to make these videos more engaging, do you want me to explain things more deeply, more clearly? Do you want me to go through more problems? Let me know. Hit me up in the comment section down below. So thanks guys a heap for sticking through with this tutorial. I'm sorry it was a bit long this time, but keep studying, keep working hard, and until next time, happy studying.